Alright, we're rolling.
Alright, so we're going to do problem 1999, mechanics 3. So it starts off with this disc over here. It has a force of tension here, and then two gravities over here. So we're going to draw our two-body diagram right over here. We've got the force of tension in this direction. We've got a rod over here, with the center of mass up here. Gravity's acting right over there, so that's going to be mg. And then we have a block at the end. Gravity's acting there as well. mg. And here's our flow. So we're going to have a sign convention right over here. This direction being positive. Let's go ahead and write our net torque statement. Net torque equals the torque of tension, so the torque of tension minus the torque of the rod minus the torque of the block equals I alpha. Alpha is going to be E0 in this case because it's in static equilibrium. It's going to equal 0. So our torque of tension is going to be tension times the radius r, because it's r away from the center. Our torque of tension, our torque of the rod is going to equal the weight of the rod, which is m, times g. But because it's a certain distance away from the center, it's going to be mg cosine theta r, because its hypotenuse of this triangle is r, and this is 90 minus theta, so it would be cosine theta r. And then our torque of the block is going to be 2m, because it's twice the mass of the rod, g. And because it's 2r away, it's going to be 2r cosine theta. Okay, so now if we rewrite those all in, we're going to have sum of the torques equals torque of tension, which is Tr minus mg cosine theta r minus 4mg cosine theta r equals 0. So now if we just solve for tension, we get tension equals 5mg cosine theta. Okay, so for part B, I'd request, okay, so for part B we're going to have to cut the string. So we cut the string out of there, so now the string is gone, and now the whole system is in motion. Alright, so the whole system is in motion, so we're going to get rid of some of this right now. Just have our net torque up there. So the whole system is in motion now. So now we're going to have to find the moment of inertia of the system before we can find the acceleration. So the moment of inertia is composed of each of the moment of inertias of each individual piece of the system. So you have the moment of inertia of the disk itself, which they've given to us as 3 halves mr squared, plus the moment of inertia of the rod itself, which they've given to us as 4/3 mr squared, plus the moment of inertia of this individual block, which is going to be 2m times 2r squared. So if you put everything over a common denominator and you solve for the moment of inertia, you're going to end up getting 65 mr squared over 6 equals the moment of inertia. So now when we write our net torque statement, we're going to have I alpha equals the net torque, which we originally found to be 5 mg cosine theta. So if we solve for the angular acceleration, we're going to have alpha equals 5 mg cosine theta all over I, which equals 30 mg cosine theta over 65, which equals 6 mg cosine theta over 13. This is our angular acceleration, however. We have to find the translational acceleration as well. So when we find translational acceleration, we multiply this alpha by r to find a. So this is over r, by the way. This is over r. Let's find a. So r in this case is actually 2r, because, well, it's 2r in this case because it's 2r away from the center. So we're going to have a equals 12 mg cosine theta over 13 as our a. Okay, now part C. Part C, we're we're asked to find the speed of this whole component right as it's horizontal to the ground. So to find that, we can use energy. So we're going to start off by saying E total equals, at the start, before this whole fall happens, it starts off up here, the block over here, a certain height above the ground. We're going to put the gravitational potential energy at this point equals 0. So PEG equals 0 at this point. So at this point, gravitational potential energy is going to equal the mass of this object, which is 2mg times the height. And the height we already found out earlier. If this is 90 minus theta, this is going to be sine 90 minus theta or cosine theta. That's the gravitational potential energy of this block, plus the gravitational potential energy of this piece, this rod piece. So it's going to be m, which is the mass of the block, times g, times, in this case it's, this is going to be 2r, 2 cosine theta, because this is 2r. So this is going to be mg times the radius times cosine theta again, because we're looking for this height right over here. Times 2 equals the energy. Okay, so we have energy total equals energy final, and our final energy is composed of both rotational and translational kinetic energy. So we're going to have E final equals 1/2 W squared plus 1/2 MV squared. And since we know what I already is, we have 1/2 65 6 mr squared W squared plus, and we know what plus 1/2. Okay. Actually, we have no translational movement here, so this can actually go away. Yeah, it goes away right now. So we have 1/2 65 over 6 mr squared W squared, and that equals to this whole quantity over here, which is 5 mg cosine theta. And now we can just solve for, mgr, that's why, mgr cosine theta. So now we can just solve for the value of w. So we go ahead and divide both sides by this quantity, and we get w squared equals 12 mg cosine theta over 13 mg r, by the way. And the m's go away and the r's go away. And now you have w squared equals 12g cosine theta over 13g. So then the w equals the square root of 12g, what?
13r.
13r, yes.
No choice.
Yeah, it's not g, sorry, it's r. It's supposed to be r squared. Yes, okay. G cosine theta over 13r, and this is the angular velocity. So we can find the translational velocity by multiplying this by r, but in this case it's 2r because this distance is 2r up here. So it's going to be w times 2r equals v, so v equals 2r times this whole quantity squared, 12g cosine theta over 13r. Put a big box around this because you're done with the problem now. 15 out of 15.
Smile for the camera.